A Carnot refrigeration cycle operates with refrigerant R134A within the saturation dome with minimum and maximum temperatures of -6 degrees Celsius and 18 degrees Celsius, and going from a saturated vapor to a saturated liquid at the condenser. The work in is 16 kilojoules and the mass of the refrigerant is 0.9 kilograms. What is the fraction of the mass that vaporizes during heat addition, and what is the pressure at the end of the heat rejection process? As usual, pause here and try solving this problem yourself before watching the solution. This is the second example for the Carnot cycles and reversible processes main lecture. The link to that 12-minute lecture and all the other examples and lectures of the Thermodynamics course are found in the description below. The first thing we need to do to better understand this cycle is to draw it in a TV diagram. We know that a refrigeration cycle consists of a low temperature and a high temperature reservoir, where an evaporator and a condenser are located, and an expansion valve and a compressor between them. We are being told that at the condenser the fluid goes from saturated vapor to saturated liquid, and we know that heat is being lost here. With this isothermal compression, we complete our Carnot cycle with an adiabatic expansion, an isothermal expansion, and an adiabatic compression. And we label the different states, and it doesn't matter which one we label as one, as long as they're consistent. So now the question is clearer. The fraction of mass that vaporizes during heat addition, meaning at the evaporator, would be the change in quality between 1 and 2. If quality is mass of vapor over total mass, the difference between x2 and x1 would be the difference between the mass of vapor between 1 and 2 divided by the total mass, which is exactly the answer to our question. And since the heat addition is coming from the low temperature reservoir, it means that we need to find QL. So we write the coefficient of performance as both QL over Wn and in terms of the temperature, and solve for QL, substituting the temperatures and the work in. And since this is a constant pressure process, this heat is equal to the change in enthalpy. H2 is HF plus X2 times HFG, and H1 is HF plus X1 times HFG. We solve for X2 minus X1. We look up the value for HFG for a temperature of -6 degrees Celsius and substitute the heat and the given mass to find the fraction of mass that vaporizes. As for the pressure at the end of the heat rejection process, since the refrigerant is on an isothermal process line within the saturation dome, the pressure at both 3 and 4 is the same and equal to the saturation pressure at the temperature of 18 degrees Celsius. So we looked that up in our saturation tables and see that it is 537.52 kilopascals. However, there's something that doesn't quite add up here. Can we really have 16 kilojoules coming in with a total mass of 0.9 kilograms? Something for you to think about. With the work-in information, we can actually calculate the mass that this cycle uses, or vice versa. With the mass, we could calculate how much work this cycle needs. Do that and notice that these two values are not compatible. I'll add this analysis as an example for this topic and link it in the description below. If you want to check out other examples for Carnot cycles and reversible processes, make sure to check out the links I left down in the description below, where you'll also find the links to the other lectures of the Thermodynamics course as well as other engineering courses. Thanks for watching.